In this tutorial, we're going to talk about scientific measurements. In this video, we are going to cover why it's important to make a scientific measurement, what are the types of measurements that can be made, what are the sources of error that will lead to mistakes in our measurements, and how do we actually then make a measurement. So on the left here, I have a picture of a woman making a measurement for cooking. And if you're off a little bit or a lot in measurements for cooking, it doesn't make that big of a deal. It doesn't lead to something that is this huge, big mistake. But then you have something like the Hubble Space Telescope right here. And the Hubble Space Telescope, if you are off by even just like 1/100th of a millimeter, you are going to have a huge mistake in the operation of that Hubble Space Telescope, and it's actually going to lead to a huge, huge problem. And that problem could cost a lot of money. Here I have an article that I found about the Hubble Space Telescope error that was made back in the 90s. You'll notice that it says that a design effect in a measuring device ended up costing a $1.5 billion mistake. And the error was human error, and it ended up just being something like a 1.3 millimeter spacing error in the assembly of the mirror, which is the optic instrument, that ended up causing this Hubble Space Telescope to not work the way it should. So they had to actually remake the assembly, and it cost a lot of money. So it's important that measurements are made correctly, especially when you're doing research, science, or engineering. In this class, it's not going to be, life-threatening or cost us a lot of money if we make inappropriate measurements, but it's good to just make the most appropriate measurement you can so you get the best results. There are actually two types of measurements that can be made. There are qualitative and there are quantitative. Qualitative measurements are non-numerical. What I mean by that is that they don't require an actual number measurement. So for example, with this picture of hot tea, a non-numerical measurement I could make is I could say that it appears hot, it's brown in color, it's steamy, etc. These are all measurements that were made without me having to use a tool or a device to tell you the measurement. It's non-numerical. Quantitative are numerical. There's a number associated with it. So if I were to actually take a thermometer and put a thermometer in there and then look at the temperature and say I measured the temperature to be 120 degrees Celsius, then now I have a quantitative or a numerical measurement. We're going to focus on quantitative measurements from here on out. All measurements have some sort of or source of error introduced into them when they're made. So no measurement is perfect. For example, if I asked you to measure the length of this leaf, you are going to make that measurement slightly different than I will. I think we would both agree that this leaf goes past the 3, and let's assume these are centimeters. So we would agree on that, but where we would disagree is what this number is, because there is no number that indicates how far past the 3 that leaf goes. So there's a certain amount of error that is introduced into this measurement, because I might say that's 3.6 centimeters, and you might argue that it's 3.5 centimeters, and so our measurements don't agree with one another, and therefore there's error in our measurement. In fact, there are two sources or two types of error that you're going to find in measurements. The first type is called random error, and the second type is called systematic error. Random error is what just happened here. Random error is human error. So random error is going to be different every time. And what I mean by that is that it's going to be all over the place. It's random. You're not going to make the same mistake every time when you're a human. You're going to maybe read that incorrectly because you didn't wear your glasses that day, or maybe you're going to see it as being slightly past or slightly before where you think the 3.5 mark is. Whatever. Random error is human error. It's mistakes made in measurement by humans. Systematic error, you're going to get the same error every time. It's consistent, and it comes from incorrect or broken, incorrectly calibrated instruments. So this is instrument error. And what I mean by that is, let's say you step on your scale and you step on it and your mass scale tells you that you weigh 120 pounds. And then you get off and you step on it again and it tells you weigh 120 pounds. And you consistently do this and it consistently tells you that you weigh 120 pounds, but then you go to a doctor and they weigh you and they say that you weigh 122 pounds. That means that your scale at home has a systematic error, or the scale at the doctor's office has a systematic error. It's off by 2 pounds consistently. And since we're talking about error, we need to talk about precision versus accuracy. So precision is how close measurements or repeated measurements are to one another. So for example, let's say I gave you a rock and I asked you and 2 other people to weigh that rock. And you each made a measurement. This is your measurement, this is your friend's measurement, and this is your other friend's measurement. Now, how we know you're weighing the same rock on the same scale, and you each got different measurements, but they're pretty close with one another. They agree with each other within 5%. And so I would say that these are precise measurements because they're close to each other. They're grouped together in a range that's acceptable. Now, accuracy is how close a measurement is to the true value. So let's say I told you that that rock has a mass of 14.09 grams. That's the true value or the actual mass of that rock. And then you can go back and look at your other measurements and you can say, okay, well, we had 14.1 and 13.9 grams. So how close are those to the true value? Well, clearly the 14.1 gram is the most accurate because it actually is the closest to the real true measurement of that rock. So it's accurate. So just so you know, with precision, if you want to get rid of error in those measurements, you would want to average them. An average of these 3 measurements actually minimizes the error that was introduced, which was, by the way, human error because each of you made a mistake based probably just on how you looked at the scale. If you want to think about accuracy and precision as trying to hit a target, it's a little easier to kind of visualize what I mean by accuracy and precision. So, for example, this target right here, if you're trying to hit the bullseye, you are all over the place. So you have low accuracy and low precision. You didn't hit the true value, and none of your values agreed with one another. Here, you're trying to hit the bullseye, you completely miss, but all of your measurements are grouped really close to each other, or all of your arrows hit really close to each other. So you're really precise, but you're not very accurate. Here, you're pretty close to the bullseye, but your grouping isn't really close to each other. So you're pretty accurate because you almost hit the bullseye, or you're really close to it, but your arrows didn't all hit in the same spot. And then, of course, here you've got both accuracy and precision because you hit the bullseye and your grouping is really tight. All right, and finally, we need to talk about how to make a measurement. So let's look at this leaf. Again, we've just seen this, so let's look at it again, and we're going to make this measurement. So the first thing you want to do is you want to look at what's the last digit on the ruler that the thing, or on your tool that the thing you're measuring goes past. And in this case, there's a 3. So we know for certain that this leaf goes past, and again, we're assuming this is centimeters, the 3 centimeter mark. It's at least 3 centimeters. Now, where this gets tricky is that this particular ruler doesn't have little graduations or little lines in between the 3 and the 4. So you're going to need to estimate only one digit past the last mark. So you're going to look at this leaf and you're going to eyeball it. And I would say that that goes to the 0.5. So then that means that my measurement, I would report my measurement as my certain digits plus my estimated digit, and then of course a unit. So all measurements need to have 3 parts. You need your certain digit, you need your one final estimated digit, and then of course you need a unit on that number. All right, let's do another example with something a little bit, or with a ruler that's a little bit more defined. And so you'll notice in this ruler that there are actually marks in between the whole numbers. So you get to be a little bit more precise or accurate with this measurement. So again, you're going to look at what you know for sure. So your certain digits, this time around you get more. So you can see that there's our measurement, that it goes past the 3, and then you've got 0.1, 2, 3, 4, 5. So there's your certain digits. In this case, you get 2 certain digits, and then of course, you have to have one final estimated digit. That's all you get, just one. And to me, it looks like it goes maybe about a little more than halfway between. You might say it goes just halfway, 0.05, and that's why it's estimated, and that's where error is introduced. And so our final measurement, when you marry the two together, is 3.56, and of course put a unit. So we were allowed our true digits, sorry, I should have made that red, our 2 certain digits, our one final estimated digit, and then of course a unit. By the way, given the choice of these 2 tools, which one would you choose? I would think that you would choose this tool right here, because you get more certain digits and less estimated, or and there's less error, I guess, because you've got more certain digits. Okay, so finally, let's talk about graduated cylinders. Graduated cylinders are a little tricky, especially when you're measuring the volume of a liquid. And by the way, these measure in milliliters, sometimes in liters. The ones you'll use in class measure in milliliters. And what makes them tricky is that you'll notice that when a liquid is in it, it makes this little curve. That thing is called a meniscus. And meniscuses happen with water-based solutions, which is 99% of the stuff you're going to be measuring is going to be something that's either dissolved in water or has water in it. So you want to make sure that you measure from the bottom of the meniscus. You never want to measure from the top of the curve right here. So no, not from there. You're going to measure from the bottom. So starting over, just to clear it up, you're going to measure from the bottom of the meniscus. So let's look at this measurement. We can do our certain digits, and our certain digits are that it goes past the 8.1, 2, 3, 4, 5, 6. So 8.6 are our certain digits. And then we need an estimated digit. So you might think that, I think it looks like it falls slightly below the 8.7, and so I'm going to say 8.69 milliliters. Now you might disagree. You might think that that falls right on the 8.7 line, in which case you would have to report your certain digits, 8.7, and then you still need an estimated digit. So you would have to add that 0. So whenever the measurement falls right on a line, your estimated digit is going to be a final 0. And one last final type of measurement, when you're using an electronic scale, something that's really nice about an electronic scale is that the last digit given to you on the scale is your estimated digit. So the scale estimates it for you, meaning that when you write this measurement down, you would not report this measurement as 93.14 and then some other digit. You would, in fact, not put an estimated digit because the scale did it for you, and you would just put a unit. So you would just write it as 93.14 grams, and your scale estimated that digit for you.